Chemistry, how are we doing today? Hopefully y'all are doing well. So today we're going to be starting our Unit 7 notes on stoichiometry. And today's lesson is going to focus on molar mass and moles. Now for this, please make sure you've got everything that you need. So paper, something to write with, your notes. You will also need a calculator and a periodic table. So make sure you've got all that, but otherwise we're going to go ahead and get started. So, like I said, today's lesson focuses on molar mass and moles. So you probably can recognize that molar mass is going to have to do with the molar masses that we find on the periodic table. So the masses of the individual elements that we have. But what is a mole? Well, a mole is simply a unit. More specifically, it is a unit that we use internationally to represent the amount of a substance that we have. Now, this is a very, very large number, okay? Very large. And so why would we use a very large number? Well, remember, we're working with very small things, right? When we're talking about atoms and compounds and elements and those kind of things, right? And so since we're working with very small things, we're probably going to need very large numbers to represent how much of each thing I've got, okay? And so that's ultimately what the job of a mole is. But it is really just a conversion. It is just a number, and that number is 1 mole equals Avogadro's number, 6.02 times 10 to the 23rd power of pretty much anything. So in a way, it's kind of like a dozen is, where I've got 1 dozen. What does that immediately tell you? What number does that immediately tell you? Well, it tells you 12, right? And so if I've got a dozen, I know that I have 12 of that something, right? A dozen pencils mean I've got 12 pencils. If I've got a dozen roses, then I would have 12 roses, right? I could also flip that around and say, okay, I've got 12 markers. I could say, well, that means I've got a dozen markers, right? And so it's, again, just a conversion that you've got there. I could also say I've got 1 week. That's going to be 7 days. Or I could say a pair is 2 of something. Or I could say a baker's dozen is 13 of something, right? And so when I'm looking at these conversions, they're just common numbers that we use. They represent an amount. So why do we use something like 1 dozen? Well, we use that 1 dozen because it's simpler than saying 12. I can go to a donut shop and say, I need 13 dozen donuts, and then they would figure out how many of those donuts I would actually need, right? So they would do the math and say, okay, well, you need about 156 donuts, right? Well, you know, donut shops are typically fairly generous, and they'll end up throwing in a couple of extra donuts for you. So when I'm looking at this, it's kind of easy for me to use these conversions just because they are, we use this to represent a larger amount than we actually have, right? And so that's the purpose of a mole. So Avogadro's number. Again, Avogadro's number is 6.02 times 10 to the 23rd power. Now, we're going to use that number enough that you're eventually going to have it memorized, but for now, it is just going to be a number that you are given. Now, yes, I recognize that on our paper here, it says 6.022 times 10 to the 23rd. That's just a little bit more specific. It technically can go on quite a bit further than just 22, but we will round it a lot of times into just 6.02 times 10 to the 23rd. So what do I use it to represent? Well, the mole is used to represent anything, really. In the grand scheme of things, it could be anything, just like a dozen could be anything. But the main thing that we focus on with our Avogadro's number is going to be how many atoms or molecules or particles or things like that, where it's a very, very large amount of something, but we use that number because that ends up being a very small amount. So 1 mole, which is 6.02 times 10 to the 23rd molecules of water, would end up being like a drop of water. Okay, like I could put it into a teaspoon, and that would be about how much is, it's 2.5 teaspoons of water is about a mole of water. And so looking at that, that's not very much water, right? but there's a whole lot of particles. There's a whole lot of molecules of water that are found in those 2.5-ish teaspoons of water. Okay? So again, it just is going to represent an amount. Now, things that it could represent, again, we typically would use it for anything, but the main focuses are going to be stuff like representative particles or elements or atoms or ions or formula units, which is specifically for ionic compounds, or molecules, which is specifically for covalent compounds. So it can be all these different things, but again, it just represents an amount. Okay. So what I actually want y'all to do is to pause my video, and I want y'all to go to this website right here. This is going to be a video that's going to kind of try to show you how big a mole actually is. And so I think it's a lot of fun to watch, but it kind of talks you through that number and what it actually looks like in terms of size, right? And so take a minute, watch that video, and then come on back to this right here. All right. So hopefully y'all have watched that video, but we're going to go ahead and move on. So how do I use the mole? How do I use that number, Avogadro's number? Well, Avogadro's number is going to be used to convert from one thing into another. Specifically, things like molecules, particles, atoms, formula units, those kind of things, right? So here my question is, how many moles of carbon dioxide are present in 4.55 times 10 to the 24th molecules of carbon dioxide? Okay, now remember this is the stoichiometry unit, right? And so looking at our stoichiometry, which remember we're going to have to like drop it low when we're doing that railroad track thing where we're converting into other stuff, we're going to use this to convert from one substance into another in the end. But for now, let's just focus on figuring out what to use Avogadro's number for. So here I've got 4.55 times 10 to the 24th molecules, MLCL is just the abbreviation for molecules, of CO2. Okay? And I'm trying to convert that into moles. So with dimensional analysis, with my stoichiometry, and stoichiometry is just going to be that number conversion, but specifically we're going to focus on atoms or elements or those kind of things. That's when we kind of talk about it as being stoichiometry. So here I've got molecules of CO2. Remember, we dropped that down so we can cancel out that unit. Why? Because we're not solving for molecules. We're solving for moles. Okay, so I'm trying to get out of molecules and into moles. So thinking about it, what ratio do I know? Well, I know that I have 1 mole, and that equals 6.02 times 10 to the 23rd. How do I know that? Well, remember Avogadro's number. For every 1 mole of a substance, I have 6.02 times 10 to the 23rd molecules or atoms or elements or whatever. So I can use that as a conversion. I can use that to convert from molecules into moles. So I can use this ratio here, this 1 to 6.02 times 10 to the 23rd. And when I do that, I've now converted into moles of CO2. So moles of CO2 is what I'm looking for. So now I can go ahead and solve. So I would do 4.55 times 10 to the 24th times 1 divided by 6.02 times 10 to the 23rd. We would get 7.56 moles of CO2. And then this would be my answer. Okay? So I'm going to go ahead and do another one with y'all. We're going to walk through it one more time, and then I'm going to have y'all do a practice problem. All right? So the next question says, how many formula units of magnesium chloride are there in 3.25 moles? So in this case, we're looking for formula units, not moles. Okay? Well, again, I can use that same ratio, right? I can use that 1 mole equals 6.02 times 10 to the 23rd formula units or molecules or atoms or whatever, right? Because the Avogadro's number can be used for anything. Okay, so let's do that. So I have 3.25 moles of magnesium chloride, MgCl2. Okay, that would be from your swap, drop, reduce. That's where I got that 2 from. And then I'm going to actually convert this from moles of magnesium chloride into formula units of magnesium chloride. Okay, so formula units would be FU for the abbreviation. And so I know that I have 1 mole for every 6.02 times 10 to the 23rd formula units. Okay? So a hint that I will give you is you're always going to put the 1 by that mole. Okay? All right. Well, I canceled out my moles, and I'm solving for formula units. So since that is what I'm looking for, I can go ahead and solve. So I would do 3.25 times 6.02 times 10 to the 23rd divided by 1. We'll get 1.96 times 10 to the 24th formula units of magnesium chloride. Okay, and then that would be my answer. All right, so now I want y'all to pause the video and solve this next problem. Okay, so pause your video, solve the next problem, and then we'll go over it. All right, so let's take a look at this. So I had 5.66 times 10 to the 32nd atoms of iron, and I wanted to know how many moles of iron that was. So 5.66 times 10 to the 32nd atoms of iron. I drop down atoms of iron, and I'm trying to go into moles. How do I do that? I do that using Avogadro's number. So I know that for every 1 mole, I have 6.02 times 10 to the 23rd. So that's what I'm going to use for my conversion. So I'll multiply by the top, divide by the bottom, and you should have ended up with 9.40 times 10 to the 8th moles of iron. All right, so now we have a general idea of how to use the mole. Again, it just represents an amount of that substance. So let's talk about molar mass. So molar mass is just going to be the mass per mole of the substance that we have. And so we already know that a mole is going to equal a certain number of atoms, right? 6.02 times 10 to the 23rd. And so it's essentially how much mass we have for that many atoms or particles or molecules or whatever. Okay? And so for molar mass, we usually write the unit as grams per mole. Why? Because it is the mass per 1 mole. So how do we do this? First step is to write your correct formula for your compound. Okay, so the very first step is to fall back on our rules from last unit. So those rules on the naming rules, right? Writing our formulas. So swap, drop, reduce if it's ionic. If it's covalent, we just write what we see. The next step is to list out all your elements separately. Now, why do we do that? Well, we do that because we're going to take all those individual masses and we're going to add them all together. Okay? Then we're going to write the number of atoms for each. Okay? Essentially, we're just going to use how many of that substance I have. And then we're going to multiply that by the average atomic mass, which we find on our periodic table. Okay? So we're going to multiply that by the mass, round each to 2 decimal places, and then we're going to calculate our answers and then add it all together. So let's take a look at this. So it wants us to find the molar mass for these 4 different substances here. So I have calcium phosphate. The very first thing that I need to do is figure out what our formula would be. So I have calcium, which is Ca. It's got a +2 charge. I have phosphate, which is PO4. It's got a -3 charge. So we swap, drop, reduce. We're going to end up with Ca3PO4 2. So then this would be my formula for calcium phosphate. Now I need to solve for the mass for the substance. So I have calcium. Calcium has a mass, based off of my periodic table, of 40.08. And we have 3 calcium there. So we're going to multiply that mass by 3. And you'll find your total as 120.24. Then I've got phosphorus. Phosphorus, again from the periodic table, has a mass of 30.97. And there are 2 phosphorus. So we're going to multiply that by 2. And we get 61.94. And then I've got oxygen. It's got a mass of 16.00. There are 8 oxygen. Multiply that by 8, we get 128.00. We take those numbers and we add them all together. And what we'll find is we have a molar mass of 310.18 grams per mole. So then this would be my answer for this problem. Okay? All right. So I actually want y'all to go ahead and solve the next problem without me helping you at all, and then we'll go over it in just a second. So pause your video, solve the problem, and then we'll get to it. All right, so first off, the very first thing you needed to do was to write your formula. So we found that we had Cl2O7. This is covalent because we've got 2 nonmetals. We also know it's covalent because there are prefixes there, right? And so now we're going to take that and we are going to solve for the masses for each individual element. So chlorine has a mass of 35.45 times the 2 gave us 70.9. Oxygen has a mass of 16 times 7, we got 112. Add those two together, we get a total molar mass of 182.90. All right. So we're going to go ahead and move on to applying this molar mass. And so I'm going to leave those 2 on the right for y'all to do as practice. So be sure to go back and double check your notes. Make sure that you've got those answers right. But otherwise, we're going to go ahead and move on. Okay. So you calculate the mole problems using dimensional analysis and the molar mass and Avogadro's numbers as conversion factors. Okay, so remember Avogadro's number is 1 mole equals 6.02 times 10 to the 23rd, and molar mass is 1 mole equals whatever that mass is from the periodic table. So my suggestion to you is when in doubt, moles it out. Now, what I mean by that is when in doubt, when you don't really know what to do, solve for moles first. Why do I solve for moles? Well, because moles is a common conversion between anything, right? And so we know grams per mole, right? Grams for every 1 mole. We also know how many atoms there is in 1 mole, right? And so we can use that as a common conversion, which means we can use it as a common place to go from one thing to another thing, okay? So when in doubt, when you don't know, moles it out. Go to moles, okay? So here's my question. If I have 200 grams of calcium carbonate, how many moles is this? Well, the very first thing we should do is to write our formula for calcium carbonate. So that would be CaCO3. Calcium has a +2 charge, carbonate has a -2 charge, so they are going to cancel out, so we would leave it as that. So how many moles is this? Well, I've got a mass here, so why don't we go ahead and solve for our molar mass, because we're going to need it. So I have calcium carbonate. Calcium has a mass of 40.08 times 1, so 40.08. That's calcium. Carbon has a mass of 12.01 times 1 is 12.01. And then oxygen has a mass of 16 times 3 gives us 48. We add all that together, we're going to get 100.09 grams per mole. Okay, so now I've got my molar mass. So now let's actually solve what the problem's asking for. So the problem is asking for how many moles is this? So I have 200 grams of calcium carbonate. Remember, with dimensional analysis, you always start with what you know. So we know we have 200 grams of calcium carbonate. So we're going to convert calcium carbonate into moles. How do I do that? Well, remember, grams of calcium carbonate is not what I'm looking for, so I drop it low. We're going to go grams of calcium carbonate into moles of calcium carbonate. So how do I do that? Well, remember, your molar mass is grams per mole. So I know that I have 100.09 grams per 1 mole of calcium carbonate. Canceled out my grams. Now I've got moles. Is moles what I'm looking for? Well, yes, it is. So now I can go ahead and solve my problem. So I'd do 200 times 1 divided by 100.09. And we would end up with 2.00 moles of calcium carbonate. And then this would be my answer. Okay, so I actually want y'all to solve this next problem where it says how many moles are there in 28.7 grams of lithium nitrate. So don't forget, first thing you should do is write your formula. Then if you've got mass, you need to write your molar mass. And then after that, you can solve. Okay, so pause your video, solve the problem, we'll go over it. All right, so let's take a look at this. So first off, you needed to convert or actually solve for the formula for LiNO3 or lithium nitrate, which is LiNO3. We do have mass there, so you are going to need your molar mass, which I solved for over here on the right, left. Wow, I'm struggling today. So I have 6.94 times 1 is 6.94, 14.01, there's one of those, and then 16 times 3 is 48. We would add all those together and we get 68.95 grams per mole. Then we come over here. We were told we have 28.7 grams of lithium nitrate, and we want to know how many moles of lithium nitrate that is. So then I will use that, convert from grams into moles using my molar mass, solve for it, and we should have ended up with 0.416 moles of lithium nitrate. All right, so I'm going to leave this next one as a practice problem for y'all to do, but we're going to go ahead and move on in our notes. Okay, so for this next problem, we're going to actually take it a little bit further. We're going to take one step further. Okay, so up to now, we've essentially been converting from atoms into moles, or we've been converting from moles into mass, or the other way around, right? But we haven't done a combination of the two. So in this case, it says how many atoms are present in a pure iron nail that weighs 13.2 grams. Okay, so now we've actually got mass and we're solving for atoms. Now, we don't know of a conversion of mass into atoms, but we do know a conversion of atoms into moles, and we also know a conversion of moles into mass. So let's actually work this problem. So it says how many atoms are present in pure iron if it weighs 13.2 grams. So pure iron is just Fe, right? It's the element from the periodic table iron. So I have 13.2 grams of iron. So that's what I'm going to start with. Start with your known, 13.2 grams of iron. And I ask myself, is grams of iron what I'm looking for? No. If no, we drop it low. Now, here's where I remind you, when in doubt, moles it out, right? So right now, we're trying to get from grams into atoms. Well, we don't know of a conversion for that. And so since we don't know of a conversion, we need to go to moles first. So moles it out. So we go in from grams into moles of iron. Well, how do we do that? Well, we do that using our molar mass. So the molar mass of iron is 55.85 grams per 1 mole. Canceled out grams. Then I remind myself, is moles what I'm looking for? Well, my question asks how many atoms. So no, it's not what I'm looking for. So if no, we drop it low. So moles of iron. Now, do I know how to go from moles into atoms? Well, remember, a mole can equal any amount, right? Any substance. So if I'm going from moles into atoms, I can do that using Avogadro's number. 6.02 times 10 to the 23rd atoms for every 1 mole. Okay, well now, is atoms what I'm looking for? Well, yes, it is. So now I can go ahead and actually solve my problem. So I'll do 13.2 times 1 times 6.02 times 10 to the 23rd divided by 55.85 divided by 1. I put all of that into my calculator and I should end up with 1.42 times 10 to the 23rd atoms of iron. And then that would be my answer. Okay, so essentially we just did the same thing, but now we're taking it a step further. We're going to actually do multiple conversions in one-dimensional analysis. Okay? All right, so I'm going to do one more with you, and then I'm going to have y'all, I'm going to leave the rest of them for y'all to do as practice. All right, so here's my question. How many formula units are there in 7.55 grams of sodium sulfate? Well, what's sodium sulfate? Sodium sulfate is Na2SO4. And we are given a mass. And so if we're given a mass, we're going to have to use our molar mass. And so I have sodium sulfate, Na2SO4. Let's break it apart. I have sodium. Sodium has a mass of 22.99. Times the 2 that I have, we get 45.98. Sulfur has a mass of 32.06 times the 1 I have. And then I have oxygen times its mass times 4 equals 64.00. All right, and now I'm going to add these together, and I'm going to get 142.04 grams per mole. Okay, so I've got my molar mass. So now let's actually solve my problem. So the question says I've got 7.55 grams of sodium sulfate. So how many formula units is that? So remember, formula units is just a fancy word for how many atoms, or sorry, how many particles I have for sodium sulfate. Okay, so I'm going to convert from grams of sodium sulfate, and I'm trying to go to formula units. But do I know of a conversion of grams into formula units? No. What I do know is moles. So when in doubt, moles it out. So grams of sodium sulfate gets dropped low. Why? Because it is not what I'm looking for, and I've got to cancel it out. So I'm going to go from grams of sodium sulfate into moles using my molar mass. So for every 1 mole of that sodium sulfate, I've got 142.04 grams. Okay, so now I'm in moles. Is my question asking for moles? No. My question is asking for formula units. So I'm going to drop down moles of sodium sulfate. I'm going to cancel out that moles, and I'm going into formula units. Okay, and I can do that because remember, a mole can essentially convert into anything, right? Na2SO4. And in this case, that conversion is for every 1 mole, I have 6.02 times 10 to the 23rd formula units. Okay, now is formula units what I'm looking for? Yes. So now I can go ahead and solve. So I'll multiply 7.55 times 1 times 6.02 times 10 to the 23rd divided by 142.04 times, or sorry, divided by 1 again, and we're going to get 3.20 times 10 to the 22nd formula units of Na2SO4. And then this would be my answer. All right. Okay, well, I'm going to leave the rest of these for y'all to do as practice. As always, let us know if y'all have any questions, but otherwise, y'all have a great rest of the day. Bye, y'all.